Okay, ma'am.
Ah,
A very good morning to all. We, on behalf of School of Computing, welcome all the participants for the hands-on session on LEX tool. I feel greatly privileged to welcome our chief guest, Dr. S. Vanitha Sivagami, Associate Professor, Department of Computer Science and Engineering, MEPCO Shillong Engineering College, Sivagasi. This session will help the listeners to gather knowledge and acquire a deeper insight of the lexical analyzer tool. Mastery in LEX will definitely aid the students in upskilling themselves to leverage this tool as support in developing higher language systems. Dr. S. Manitha Sivagami is an expert in the area of formal languages and automata theory and compiler design. She is a top-notch achiever in the above mentioned area apart from image processing and systems programming. She has around 23 years of teaching experience. Her research work are published in several national and international peer-reviewed journals. Her excellence in research is well portrayed and appreciated in many conferences. Ma'am, we are very happy to have you here. Now, the stage is yours.
thank you, sir. So,
Thank you,
dear
ma'am.
participants, this morning session we will have here overview of the lexical analyzer generator. A special tool we are going to discuss today is LEX, and so we are just going to have the how to work with LEX. I think all of you will be familiar with the compiler construction basics. So the concepts behind the lexical analysis process, I think all of the students will be familiar with. Uh, is anything to be added to the concepts? Saranya ma'am?
No, ma'am. Ma'am, you can proceed with Lex tool, ma'am.
Ah,
So we are
yes,
nearing
yes.
the 50 units, so people will be knowing the
Ah,
fundamentals, ma'am.
okay, okay, okay. So shall I share my presentation, ma'am?
Yes, ma'am. Sure, ma'am.
Okay. I'll share my screen itself because I may show some code working also parallelly.
Okay. Okay, ma'am.
Mm. So I am sharing my screen. So is my screen visible, ma'am?
Uh, yes, ma'am. 1 minute, ma'am. I have to. Yes. 1 minute. Ma'am, it will take just a few seconds, ma'am. It will be.
Yes.
Yeah, it's now visible, ma'am. Visible to the participants also.
But for me, some multiple window views
Yeah,
there
yeah,
may be
yeah, ma'am.
seen.
It's the same way for us also.
Okay. Okay, ma'am.
Can you just stop sharing and again? Yeah, now it's fine, ma'am.
Yes. Shall I put a full screen view, ma'am, of the PPT?
Uh, yes,
Or
ma'am. I think there is a delay, but okay, we'll wait for 2 seconds. Yes, ma'am. Now you can put full screen.
is a full
Yes,
screen
ma'am.
view visible, ma'am?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. So today's session we are going to see how to work with the lexical analyzer tool LEX. It's a very simple tool to learn. So you need not put high more efforts to learn this tool. It's very easy to learn this tool. And using this tool, we can do the construction of the lexical analyzer part of a compiler very easily. Okay. So when we are writing the same process by using some high-level languages, lexical analyzer construction will be very tougher. But by using this tool like LEX, it's very simple. So actually, this is one of the compiler construction tool which can be used in parallel with another tool known as YAK. Okay. So Yak is nothing other than the tool which is used for building the parser, the other parts of the compiler. So it can do the machine code generation, intermediate code generation, all those parts. So this LEX tool is used as a what I can tell is supporting tool for Yak. So Lex and Yak together, we can very easily build a full compiler itself. To generate the lexical analyzer's other name is scanner, we can make use of this Lex tool. Students, if you want to ask any queries, you can ask at the time, or at the end also we can have a separate question session. We can have a question session at the end. Okay. So here you know that the general job of a lexical analyzer is the first and foremost task in compilation. So compilation, whenever we are feeding in a high level language program, the compiler translates that high level language program into an assembly code or machine code. At that time, the first and foremost operation by the compiler is reading the source code and breaking the source code into lexical units. The lexical units are in turn also known as tokens. So we also name this process, the major job of a lexical analyzer is token separation. Okay. So your input program will be a stream of characters. You normally, whenever you type a high-level language program using some editors, we type it as a text file only. So the input program in high-level language is a stream of characters. This stream of characters, where it is separated into lexical units, the process is known as lexical analysis. And this lexical analysis tool, the tool that performs this lexical analysis is known as lexical analyzer or lexer. And now the lex is a tool which is used for generating a lexical analyzer easily. Okay. And it can be used not only for lexical analyzer development, for any other operations which work with the stream of characters. So for example, from your given document, I want to make a pattern searching. For example, I want to extract the hyperlink tags from my source code, from a given document. In that case also I can make use of the lexical analyzer. Okay. So lexical analyzer is not only, this lex tool is not only used for lexical analyzer generator. Whenever you want to work with the stream of characters also, we can use the same tool. Okay. And this is a tool compatible with the Linux operating system. There is a Unix or the Linux operating system, but we can have what I can tell is the equivalent compatible tool to work with in Windows operating system also. Actually, this Linux environment setup, this Flux environment, Lex is a tool. Equivalently, we can have many versions of Lex, such as FLEX, Flux, VLEX, VLEX. So many other versions are present. So in that, the FLEX, the Flux version of lexical analyzer, can be even implemented in the Windows operating system. We are having a equivalent tool for that. So not only in Linux operating system, in Windows operating. So today's session I am going to show you some demo of Lex programs also in this Windows operating system based Flux environment. Okay. And what is this Lex? In turn, it is nothing other than it is a program. Program meaning it is used for changing one form into another form. So this can also be specified as a compiler. So this yellow color box, now green color box or yellow color box, this specifies that Lex is a compiler or a program which reads our specifications and changes that specifications into a lexical analyzer or lexer. Okay. So this Lex tool is now going to generate an output in C as a C. So actually this Lex code is very easy to learn. The main point is nearly 60% of the Lex code will be a C program only. Remaining 40% only will be your Lex code. So it's more or less compatible to your Lex and Unix environment settings. Okay. So you can see that Lex specifications will be giving you the pattern specifications of each tokens which we want to separate. You normally know that pattern specifications can be given by using regular expressions. So the regular expressions are given as input to the Lex program, which are converted into a lexer. Lexer is nothing other than a C implementation of a finite automata. You normally know that a finite automata, that is a DFA or an NFA, is a machine which is suitable for implementing a lexical analyzer. So this particular tool is used for transforming a regular expression into a C program, which is none other than a working similar to operation of finite automata. Okay, it is used for describing the patterns. The first and foremost point is the Lex program. When you want to store it as a file, the file should be having the extension L. So just as a C program has the extension C, the LEX program should have the extension L. Okay, and the LEX program has some structure. Okay, so this structure of the LEX program, as you specify, it has three different sections. The names of the three different sections are definition section, rule section, and user subroutine section. Okay, so the three sections, what are they? We are going to see. The same structure is also applicable for the YARC tool also. So whenever we are building a compiler, together we use LEX and YARC, and in that case, YARC also follows the same structure. Originally, YARC is only having the structure. LEX has actually borrowed the structure from YARC. Okay. So this, how to differentiate that this part is a definition section, this part is a rule section, this part is a user subroutine section. We have the delimiter in between each and every section, which is none other than percentage. So between the definition and rule section, we have a percentage. Between rules and user subroutine section, we have a percentage. And out of these three sections, you can see that in a LEX program, the rule section only is an essential or a mandatory session. Okay, the remaining sections are optional. If in your LEX program you don't require any definitions to be given, the definition section can be left out. If in your LEX program you don't require to write any subroutines, in that case the user subroutine section can be left out. Okay, but the rule section is a core part of your LEX program, which includes the regular expression, which is giving the token specifications. Okay, and this rule section is essential. So for example, if in your program you have only the rule section, will not be having the definition section. In that case, the program should start with percentage, meaning that what I am typing now is not the definition section. What I am typing now is the rule section. After the percentage, if you are typing, it is the rule section. And if your program does not have the user subroutine section also, the second percentage is not at all required. So the second percentage is required to be typed only when the user subroutine section is present. And one more important point to emphasize is, as I already specified, a LEX program will be having a mixture of LEX code along with the C code. And you know that C compilers, you will see work with many C compilers. Marketly, we have many C compilers. Whatever C compilers, the flexibility of the C compiler is C has many advantages, features such as it supports, it is easily portable. The program is having what you can tell is the indentation is not a matter. That is, in a program, you can type a single program in a single line itself. If your program is having some 10 instructions, even the 10 instructions can be typed in a single line. Or even a single instruction can be typed in 10 lines. That is the flexibility in C compilers. Okay. Indentation is not a matter. Each and every line of code you can type in any place of your editor. Okay, that is in any column you can type. But that is not the case for the LEX code. LEX code always is giving importance for indentation. This information should be typed in first column. This information should not be typed in first column. Likewise, we have to differentiate when we are using the LEX code. So remember, your LEX program is a mixture of both LEX code and C code. So C code we need not give the concentration of indentation, but for LEX code part we have to give the concentration for indentation. If you want to clearly tell, this LEX compiler, as I showed in the previous slide, it will be reading the specification, it will be transforming that into a LEXer. So, but our input program, which is the file with the extension .l, which will not only include the LEX specification, it will also include some C coding, I told you. In that case, the LEX specification alone will be processed by the LEX compiler. The C code will be just copied into the output. So now the main task is the LEX compiler only processes the LEX code. So LEX compiler, whatever you want to process, you have to differentiate that by specifying in the first column. Okay. So from this you can understand that this delimiter is also a processing required by the LEX compiler for differentiating whether this is the definition section or rule section or user subroutine section. So this delimiter percentage even should be typed in the first column. Okay. So that is a very important thing. Indentation is very important when you are typing a LEX program. So let us now see what are the contents of each and every of these sections. So first, the definition section. So definition section, as we can know that here again we can have a mixture of LEX and C code. So we can have C definitions. C definitions meaning, for example, variable definitions, that is variable declarations, initializations, functional prototypes, okay, header file inclusions, constant definitions. All these things you can do it in the definition section. Similarly, LEX definitions also we can do it in the definition section. Okay, and here one point, the compiler we have to differentiate whether it is a C definition or LEX definition. As I specified, normally you can differentiate it very simply as if I am typing the definition from the first column, it is a LEX definition. If I am leaving the first column empty and typing in other columns, the definition is a LEX C definition. Okay, so definition first column, if it is starting, it is a LEX. If it is not starting in the first column, it is a C definition. But we can have some exceptions also. One such exception is like this: if I am using a special delimiter such as percentage open curly brackets and percentage close curly brackets, within this particular end points, whatever we type, wherever we type, it is a C coding only. In this case, within the brackets, even if I am typing in the first column, it can be a C code. But if I am not at all using this particular delimiter, you have to be very careful. First column, if you are typing, it is taken as LEX code. It will be processed by the compiler. First column, if I am not typing, it is taken as a C code. It will be just copied by the LEX compiler. Okay, so that's the thing. When I'm showing examples, I'll give it. Okay, the next important section is the rule section. The rule section only is going to give you the token specification. So rule section, as we specified, it is a collection of rules, and each and every rule is of the following format. Each and every rule has two informations. One is known as a pattern, other one is known as an action. So pattern is nothing other than the regular expression format for a given token. Action is nothing other than what we have to do when this particular pattern is viewed by the lexical analyzer. So you know that the lexical analyzer can do many tasks. For example, a lexical analyzer can separate tokens. It can eliminate the comments because it is the first and foremost phase of the compiler. Comment processing, comment is normally for the documentation purpose when you are typing comments in your program. So comments are need not to be processed by the compiler. So comments removal, white space, for example, for languages where we don't give any importance for indentation, white space characters such as blank tab removal. So that removal also has to be taken care by the lexical analyzer. Okay, removal. Then what others is errors, finding out errors, making a symbol table entry. We can have many tasks to be done by the lexical analyzer. So what task you are going to do for a particular pattern? For example, when I'm coming across a new line, just to count the lines, because normally you know that the compiler will be displaying the error messages, and in the error messages it will be displaying the line number of the error also. So when you want to count the lines, whenever we are getting a new line character, we can do the corresponding action as line counting. We can have a count and we can increment that. Instead, if the given pattern is a pattern of an identifier, then the corresponding action is pass the information about the identifier into the next phase of the compiler, or identifier should be stored in the symbol table. In that case, the corresponding action to be done for an identifier is store the identifier in the symbol table. When it is for example, a keyword, just I want to intimate the compiler's next phase that it is a keyword. This particular keyword is it. We need not do any other task. So for each and every type of token, the job to be done by the lexical analyzer may differ. So that is known as the action. So action is what is the current job the lexical analyzer has to do when there is a pattern matching in your given input. Okay, for example, your given input is a source code. Source code, when it is matching with a particular pattern, what action we have to do, that is given as action. And in this LEX program, this pattern is to be given in the LEX format. Since it is in the LEX format, this particular pattern should begin always from the first column. As you know, LEX code should be given in the first column, whereas action is purely C code. Okay, pattern is LEX code, action is C code. So the LEX compiler only will process a pattern. It will just copy the action to the output. Okay, and each and every rule can be given in a separate line. Okay, so now you can see that some particular cases more than one pattern can have the same action. For example, I'm having some 10 keywords in my program. For the 10 different keywords, I want to do the same action. In that case, I can give all the 10 different keyword information in the single line pattern and the corresponding action. Or for each and every keyword, I can type this pattern in a separate line. In that case, I can write a single action for all the patterns. So what I have to do is I have to type the first pattern, end the sentence with pipe symbol. The next line pipe symbol, that is the pipe symbol is nothing other than the symbol which is present above the entry key. Okay. And second line I can type the next pattern, pipe ending with pipe symbol. Third line I can type the third pattern ending with pipe symbol. So if I'm having a 10 patterns, 10th line I will be typing the 10th pattern. There I can write the corresponding action. And one more important thing, that between the pattern and action, compulsorily we should have a delimiter. The delimiter, since it is a Unix environment tool, the delimiter can be white spaces. That is, the delimiter can be any number of blank or tab. Okay, between a pattern and action, you should have at least one blank or a tab. Okay, that is a very important point. And in this case, for multiple patterns, when you're having an action, you have to follow like this. But in some cases, your action can be multi-line, bigger action you can have. So in the case multi-line code, you have to type in action part. So actually, once you start the curly brackets, after this, whatever you type, even in multiple lines, the coding will be taken as an action. Once you're ending this close brackets only, the LEX compiler will understand that the action is over. Okay, so no need of. So in some cases, if the action is in a single line, we don't require this brackets. Curly brackets is required mainly when we are working with multi-line action. Okay, I will show examples. The last section is a user subroutine section. This user subroutine section is mainly going to have the C code. Okay, so it is going to have a C code. It can have variable definition, function definitions, main function definitions, everything it can have. But this section, it is not processed by the LEX compiler at all. It is just copied to the output. Okay. So I will now show you how your LEX compiler is going to operate. As we already saw, the LEX program has three sections. The important section is the rule section. This rule section is converted into the lexical analyzer. And this lexical analyzer is again a function, a C function. So the name of that C function is YYLEX. This name is fixed. Similarly, the name of the output file is also fixed. The input file, I can give my own name. For example, I can give the input file name as sample.l. I can give the input file name as expression.l. I can give the input file name as control statements.l. So input file name I can choose just with the extension .l. But the output file name is always lex.yyc, which is created by the LEX compiler. And in this lex.yyc, this yylex is one of the important functions, which is nothing other than the translated part of the rule section. Okay, and you can now understand that when we are compiling the C program, we can now generate a lexical analyzer because output is now a C program. Directly we cannot execute a C program. Again, we require a C compiler for executing this C program. So even though we are using a LEX program, we require two-step process. One-step process is after typing the LEX program, you have to compile the LEX program using a LEX compiler, and the output will be generated as lex.yv.c. And after doing this, the C compiler should be called with lex.yv.c as the input program, and the C compiler will be generating you the output exe executable, which is none other than the lexical analyzer generator. Okay, this lexical analyzer generator can be used for token separation. Okay, so now let us see a very before let me slightly minimize this PowerPoint show and show you a simple LEX code. Before that, we'll see some more slides. Okay. So the lexical pattern matching process, how it is done by the lexical analyzer, let us see. So the lexical analyzer, it reads the source code for a pattern match. It is just a string. Pattern matching is a string matching process. Okay, whenever there is a pattern match, the lexical analyzer, as I have already specified, for each and every rule we have an action. No, the corresponding action will be executed. Okay, as I already specified, for a particular token, you want to do a symbol table entry. The symbol table entry action will be executed. For a particular token, you want to do the line counting. That action will be carried out. Okay, so user can add what action to be done as a C code. Okay, one example as I specified, line counting, error reporting, weight space removal, everything can be written in this code. And you know that in your LEX program, you can have multiple rules for each and every pattern. You can have a separate rule. Okay. One point is you should not have conflicts when you are specifying rules. Conflicts means for a same pattern, I cannot write two different rules. See, now in this case, I am having two patterns. This is a pattern, island is a pattern. Here I am taking a string pattern. Okay. So you can see that in this pattern is we are having two characters. In this pattern island, we have 6 characters. But anyhow, out of the 6 characters, this is a substring. Within this pattern island itself, I'm having the substring is also. So actually, when I'm writing two different patterns rules, two different rules, one rule for recognizing the pattern is, and one rule for recognizing the pattern island. And during the processing of a sentence, let me assume that I'm giving the sentence as this is an island. So you can see that the first word like we are having a pattern this. In this case, this pattern matches with the first case, this, even though it is a part of a string. The second pattern is also matches with this. But the third pattern match in the given sentence, island, it is matching only with the second category. The reason is the lexical analyzer always identifies the longest pattern match. So when it is immediately seen in this case, in this given word also, this is the first 2 characters, but immediately it will not match that with the pattern is. It will be finding out the longest pattern match, and that pattern match only will be resolved. So when you're having conflicts among 2 different patterns with different lengths, the longest match will be considered. In any order you define. So for example, if in your program I'm having some 10 rules, if I'm writing the is rule as the first rule and island rule as the second rule, also in this case for this pattern pattern only will be matched. If I am writing in the reverse order, that is I am writing island rule as the first rule and is rule as the second rule also, the pattern matching will be done for island only. Okay, so this will be now the how the lexical analyzer treats for the longest pattern. But if in your example you are having patterns of two different patterns of same sizes, then how the LEX resolves that? See here in this case, I am having 2 different patterns. One pattern is, another pattern is this pattern. You know that it is used for mentioning a character class. Okay, so this character class pattern now specifies that in this pattern, it matches with any single alphabet, small alphabet A to between A to Z, and the second character also specifies it matches with the single character A to Z. So here again you can see that the first pattern is explicitly specifying the pattern is, the second pattern is specifying 2 characters, 2 lowercase characters. So if I'm seeing now, in this case, in my program, I am having a given sentence as visitor program. So the word is, it matches with which of the patterns? It matches with the pattern is if it is defined in the first rule. Okay. Actually, among these rules, for example, I am assuming that this is pattern is defined in the 5th rule and this second pattern is defined in the 7th rule. Which pattern defined first? This pattern only is defined first. In that case, now the LEX favors in case of the first pattern is. Instead, if this pattern is defined first as a 3rd rule, this pattern is defined in the 5th rule, LEX favors in case of this pattern. So when you are having a conflicting between patterns in 2 different rules of the same size, then LEX always resolves in favor of the first pattern. Okay, first rule. Okay, that's the thing you have to consider. So this is how the LEX resolves the conflicts. So now these are the important commands we want to use in the Linux environment for working with the LEX program. As I already specified, your LEX program should be typed with the extension L. So for example, if your LEX program is sample.l, so now the command for invoking the LEX compiler is LEX space sample.l. So this command will now process the LEX program and generate the C program as lex.yy.c, which is having a lexical analyzer. And remember, when this translation is done, the LEX compiler, if it is finding some mistakes, it will be reporting the errors, but no errors will be reported in the C part. Okay, because the C part is just copied. Okay, later the output C program should be again compiled by the C compiler. For example, in this scenario, I have used a compiler known as a GCC compiler. C compiler, whatever compiler you want, you can use. So GCC compiler, I am invoking the command as CC. So CC is used for invoking the GCC compiler and the file name, and this minus LL is nothing other than linking the given output with the LEX library. Okay, normally when you are working with the C program, for linking with the Mac library, we will be using minus LM. Likewise, for linking with the LEX library, we have to use minus LL. Okay, so these are the very 2 important commands. The first command is used for invoking the LEX compiler, which generates the C output. The second program is for making the executable ready. That is, C compiler is used by compiling the C program and generating the output. Okay, you know that the output generated will be A dot out. Okay, so since YVLX is a lexical analyzer, the very important task to be done is in your C program, in the main function, we have to call YVLX. Okay, main function when you're calling YVLX only, it will be executed. So if the user wants to perform other tasks, then he has to write it within your main function. By default, if your main function is just going to have the call of YVLX alone, we need not write the main function. The reason is LEX compiler itself will automatically generate the main function. I told no, you need not write the user subroutine section. So if in your main function I'm just having main function only one line I'm having calling YVLX, I need not write the main function. LEX compiler will generate that. But instead, if I want to do some other operations, I have to write the explicit main function. Okay. So for pattern specification, we require the regular expression format. Regular expression format is just following the pattern rules as in the Unix environment. Unix, if you have worked with the grep command, in the pattern matching commands, you would have seen such meta characters. So those characters only we are going to use it here. So let me show some meta characters which are used for pattern matching, pattern specification. So the first character is dot. Dot now specifies it is matching with any single character other than new. Star, no, 0 star when I'm specifying it is 0 or more occurrences. A star when I'm specifying it is 0 or more occurrences of A. Okay, so that is it. And plus is a positive closure. A plus if I'm specifying it is 1 or more occurrences of A. A question mark when I'm specifying it is either 0 occurrence or 1 occurrence of A. Square bracket already I showed no character class. When I want to specify within square bracket, if I'm having A, B, C, D, what is the meaning? It matches with A, B, C, D. That is, it is equivalent to write A, R, B, R, C, R, D. R normally we specify by using the pipe symbol. Okay, so that is the thing. Let me write some sample. Wait, let us have it. Let me show you a sample code. We can even use a notepad editor for typing LEX code. Okay, so let me now show you. See, for example, if I'm using the pattern ABCD, it now means that this pattern matches with either A, RB, RC, RD. Okay, this is the meaning. So instead of writing such a lengthier pattern, I'm writing like this. I can even write this more shortly, like A to D. What it does now, the LEX compiler checks for the ASCII of A, and starting from ASCII of A to ASCII of D, all the characters present in this range will be taken. Okay. So only the previous example I took, no, A to Z when I'm taking, it considers all the lowercase alphabets. For example, if my pattern should consider either a lowercase alphabet or uppercase alphabet, I have to write my pattern like this. Remember, within the square bracket, I should not use any delimiter. In between the lowercase alphabet and uppercase alphabet, I should not leave a space or I should not give a comma. In that case, the space and comma also will be taken as characters for matching. Okay, so I have to specify only the range of characters is either falling within the lowercase alphabet range or uppercase alphabet range. Okay, so let me tell you how to write a small group. For example, I want to write a regular expression for identifier which begins with an alphabet. Okay, so which begins with an alphabet. The first character of the identifier is an alphabet. And additional characters, it can be followed by either alphabets or digits. Okay, in that case, I can specify alphabet or digit. And you can if your identifier should begin with an alphabet and it can be followed by any number of alphabets or digits. Any number of interval you can have 0 or more occurrences. So that can be indicated by the star. So the star indicates that this character, alphabets or digits, we can have any number of occurrences, whereas the first pattern is compulsory. So now this is how to write a regular expression for identifier easily. So this identifier now pattern specifies it begins with an alphabet. It can be followed by any number of alphabets or digits. Okay. Let us now see how to instead of having this square bracket, if I'm having a square bracket with the cap symbol, the meaning of this square bracket is now the given character matches with any ASCII character other than these four. So previous character, if a character is one among these four, it is considered. In now, since I am using the special meta character cap, it now specifies that if the given character is not in this collection, it is matching. Okay. If it is any other ASCII character other than alphabet, if it is not in this range, it is matched. Okay. So that's this thing specified here. So it matches with the given character. Here a hyphen is used for specifying the range. When I'm giving cap as a symbol, it does not match any character from the class of characters. Instead, I can give this cap not with, if I'm giving the cap within square bracket, it is having a different meaning. If I'm giving a cap without square bracket, for example, if I'm giving a pattern like this, in this case, it now means that the given pattern is hello, but the cap in the beginning indicates that the hello should be present at the beginning of the sentence. For example, if I'm having hello, 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 so for example, if I give a given input, you can look at the given input. The given input has 5 hellos. First line has 3 hellos, second line 1 hello, third line 2, 1 hello. Totally 5 hellos. But this pattern, when I'm specifying, it matches only with the first line first hello and the second line first hello. Because this special meta character cap indicates that the hello should be present at the beginning of the sentence. The hello which is present in the middle of the sentence or in the end of the sentence will not be considered. Okay. So in other case, it matches with the beginning of the sentence, not the one that is in the succeeding the new line character. Okay. Dollar. Similarly, dollar is used for indicating the pattern which is present at the end of the sentence. Okay. So if I'm giving hello dollar, in this case, instead of giving cap hello, if I'm giving hello dollar, it matches with only 2 hellos again. It matches with this hello and it matches with this hello, because both these hellos are only present at the end of the sentence. Remaining hellos are present in other parts. So in that case, dollar will be matching. Okay. And N1 to N2. Normally we know that when I'm giving star, when I'm giving A star, it indicates 0 or more occurrences of A. A plus, it is 1 or more occurrences of A. A question mark, it is either 0 occurrence or 1 occurrence of A. If instead I'm giving A 2, 4, it is matching with minimum 2 occurrence of, that is, it matches with AA or AAA or AAA. That is, it matches with minimum 2 occurrence of A to maximum 4 occurrence of A. I can restrict the minimum and maximum occurrence. In these cases, the minimum occurrence is restricted to 0, but maximum occurrence we can have until infinity. Similarly, here the minimum occurrence is restricted to 1. Maximum we can have infinite occurrence. But in this case, if I am specifying, it is, we can have minimum 2 occurrence to maximum 4 occurrence. You can even have like this, A5. This now specifies, we don't giving a range. So this specifies the given pattern should match exactly with 5 occurrences of A. Specific occurrences of A, when I want, I have to use like this. Okay. So N1, N2, when I'm specific range of occurrences. But if I'm giving a single number, it matches only with a single occurrence. This pipe symbol already is specified for this or that. For union operation, we use. So that is known as a pipe. Okay. And this brackets always used for grouping. Curly brackets, you can even have this curly bracket explanation I will give later. Let us write a small program. LEX program, we are going to write the first LEX program. So let us see, this first LEX program is having only the rule section. It's going to have only one rule. Okay. So since it is going to have only the rule section, no definition section, the program should begin with percentage. And this rule is so this rule now specifies when the given pattern, what is the pattern I have specified? Either a blank or a tab. Within square bracket, whatever characters I am giving, it is taken. So this is a blank. Here I am having a blank character. Here I am having a tab character. Okay, tab is indicated as backslash. And you know that I am giving a semicolon. Remember, this now is a pattern. The square bracket, what I am giving is a pattern. Once I am giving a space, the part after that is taken as an action. So here the action is now semicolon. Semicolon meaning it is a null action. Null action means nothing will be done. So actually this program is nothing other than in your given input. When I want to remove space and tab characters, okay, I want to give the particular rule. Remaining characters, normally you have to understand one thing, always will be having some defaults when you are working with the LEX compiler. When I'm not specifying any action or any pattern, so in a given sentence, you are having a set of characters which do not match with any of the rules in your program, then always the default action will be carried out. The default action is displaying the character in the screen. Okay. So now in this case, I'm having only one rule. So the rule specifies that in this program, when you're having a blank character or a tab character, do no action. In all the other cases, there is no rule specified. So for the remaining characters in the input, just it will be displayed. So this program is going to do a very simple job. Whenever in a sentence I'm having other characters, it is going to display the characters. Whenever in the given input I'm going to have blank or tab, it is going to remove those blank and tab. Okay, so this particular program is a white space removal program. So let me now show you how this program is going to execute. So this program is now to be saved. Okay, let me have this program. I'm having a Flux environment for working. First for just for your visibility, I'm typing the program in Notepad. So this Flux environment, I have created a new LEX program. See here, this new LEX program is having the rule that I have specified. Actually, in this text tool, we are having these options. So these options are now you need not worry about. You can see that in this LEX program, I'm not having, actually, I don't require this statement even. If you want, you can remove that statement. This particular part, as I already specified, it is going to indicate that it's a C definition. Before the first percentage it is occurring. So C definition, I am just including stdio.h. C whenever you are having a printf or scanf or IO statements, we'll be using stdio.h. But in this program, I'm not having any such statements. So if you are omitting this, even it is going to work only. But in all the other programs, and I'm going to print something, okay, I require. So just this line is now indicating within the curly brackets, whatever I'm typing is a C code. Okay, even if I'm typing in the first line, first column itself, no problem. And once I'm getting this percentage, I'm having only one rule. So this rule now specifies that when it is a blank or a tab or a new line, just do null action. Even new line I can omit. Blank or tab, because the input is going to be only a single line input. Okay. After percentage, we have the user subroutine section. So the user subroutine section indicates the main function, because you know that the output when it is converted into a C program, strictly it should have a main function for execution. So the main function just calls YVLX. It's not going to do any other task. Okay. So let me save this program as remove white space appears. I'm saving the program as remove white space.l, and now you can see that I can use the tools and compile this build to the LEX program. So LEX program compilation. Actually, since it is a Windows environment, I need not use a command. I'm just using icon based. I have compiled the program. Okay. So the normal termination. If you're having some error messages, it will be printed in the bottom part. Again, this tool. I will give you the link of this tool at the end. And then I have to build the LEX file. It's not. Errors are printed, but I'm not getting an answer. me execute this program and show you. Yes, it's not executing. So for execution, always you know that the LEX compiler, it's built for the Unix environment. Unix environment always the input will be read from the standard input device and the output will be displayed in the standard output device. So standard input device is a keyboard and the standard output device is a monitor. So the LEX compiler also takes those defaults. So defaults are it reads the input from the keyboard. So now once the lexical analyzer is generated, it reads the input. Okay. So this is my, I'm typing my first LEX tab, any number of tab and space you can type. Once you're pressing the enter, you see that the output level, all the blank and tabs are running. So that program only we have written, removal of blank and tab. So blank and tabs are running. So again, it is now waiting for your input. Hello. Hi. So from this you can understand that the default behavior of the LEX compiler is it will be again and again getting input from you until you quit the execution environment. So it will get the input from the screen keyboard. It will process the input once you press the enter key and it will display the output in the screen. Okay. So that's the default behavior. I have closed the output. So this is how the LEX compiler is going to operate. Okay. And now in the previous program we have seen that how to read the input from the keyboard. But normally when we are working with the programs, our input, when you want to work with the compiler, input will be in a file. So how to read the input from the file? For that we have to depend upon the LEX library utility known as YYIn. YYIn is nothing other than the input stream corresponding for the lexical analyzer. So Lexer always reads the input from YYIn. By default, YYIn is set as stdin. So only it reads the input from the keyboard in the first program. But if I want to change the YYIn, I can write my main function like this. See here what I have performed. In the command line arguments, I have now read here file name. So now what I am doing, from the file, I am reading the input and the file is opened in the read mode and the file pointer is assigned as YYIn before calling YYLX. All these tasks should be done before calling YYLX. Once before calling YYLX, these operations are done. The input will not be read from the keyboard. Instead, input will be read from the file. Okay. So now I'll show you how it is operating. So in my main program, let me even get the input directly from the user. Okay. So let me open the file YYIn. When I'm using YYIn, I have to type in the C section extern. Actually, YYIn is a utility which is defined by the YAC compiler. So when I'm using YYIn within the LEX code, I have to define it as an external variable. Okay, you know about the external storage class. The variable which is defined in another program can be used here. So external, I can use it. Okay, so external file star YYIn. Now I can use this YYIn. YYIn equal to F4. Let me take that my input. So input program I'm having in sample.txt. I'm opening the input file in read mode. Then I am calling YYLX. Okay. So once I am saving this file, let me create now in the same folder. This folder, let me create a notepad file which is having an input. Okay. This is my first LEX program. Hello participants. So I'm saving the file name as sample.txt. Yes, in the same folder. The same folder I'm saving the input file. So now when I'm invoking the tool, the same program, I'm compiling the program, I'm building, and I'm opening the command prompt. So see here, it's not recognizing sample.txt. This file name is sample.txt only I have created. Yes, it is in the same folder. Executable is created. See, the executable is present here. It's okay, let me print. Okay, let me show you how to print the output also in a file. Let's check together. Maybe out is now the output string corresponding for output. So when I want to display the output also in a file, let me have it as output.txt, out.txt. Okay, some issues are there. I'll check it. But this is a command. Okay. Okay, so this will work actually. So the in is now the input stream, which is corresponding for the specifying from where the input should be read from, and out is the output stream, which is corresponding for from where the output should be read. The output should be written into. Okay, and some other macros we can see that echo is one macro. It is now going to specify when I want to just display the token into the output, we can use echo. Echo is nothing other than a Unix macro, no? So the same macro, we can use it in this LEX code also. And YYL is val, YY lexical val, that is meaning of YYL val. This is a very important attribute which is used by the lexical analyzer when it want to return some information to the parser, and when you're going to combine the operate with Yak. Yak code, when you're going to combine the operate, we will be needing this YYL val. Okay. And YY text is nothing other than the identity token. Let me show some piece of codes. So this is a program I showed you now. This program I have added one more rule. See this, the first rule specifies I have to omit the blank tab and new line. The second rule is dot. Dot now specifies other than this, if I'm having any character, just to print the character. Even if you're not specifying the second rule, I have got the same response. The reason is the default action itself is display only. Okay. So this is one more program. I'll explain this program. So in this program, we are using a LEX definition. So how to use a LEX definition? See in this pattern, I'm using now curly brackets. Curly brackets is whenever I'm having a regular expression which is very lengthy. So that regular expression can be given with the name. So for example, you can see that here this pattern is now specifying a digit 0 to 7. So 0 to 7 digit, it is specified as corresponding octal equivalent. The character class on the backslash 60 meaning the octal equivalent of the octal ASCII equivalent of 0. Backslash 71 is an octal ASCII equivalent of 7. So 0 to 7, the numeric 0 to 9, sorry, after the unit of 9. So 0 to 9 digits I can represent by using the name number. Similarly, lowercase alphabet, uppercase alphabet, capital A to Z. Okay, I can even write like this. So for example, if I'm writing now, square bracket capital small a to z, capital A to Z. If I'm having this pattern, instead of using this pattern, I can have the name alpha. So what is now the name? This particular pattern specification giving instead of using this lengthy expression, if I'm giving this name, the pattern is going to be replaced. Just like a hash define statement in C. Instead of using a constant, I can have a name. Yeah. So instead of giving a regular expression, you can give a name for that. And once I'm giving the name, the pattern will be replaced. Okay. And see here, instead of this pattern. So remember, the definition of the pattern should be given in the definition section, not in the rule section. Definition section, before the first percentage itself, I have to specify that for this particular pattern, this is the name. For this particular pattern, this is the name. Then only within the rule section, for specifying each and every pattern, instead of the particular pattern, I can use a corresponding name enclosed within curly brackets. So in this case, you can see that we are having some 3 rules. So 4 rules, actually 4 rules. So I will show it in the slideshow. So this actually one rule is hidden. The first rule is now the blank tab removal rule. The second rule is the number. Here you can see that if I'm having more number of characters, when I want to do a length restriction I can do it in the pattern also. Pattern I can specify that the number of characters should be only maximum 3. I can give 1, 3. Instead of giving 1, 3, in the action part also I can restrict the length. How I can do that length is, I'm having one utility known as YY length. YY length is nothing other than the length of the recognized token. So the length of the recognized token when it is greater than 3, I can now actually, since I'm writing a LEX program alone, I'm just displaying messages. But when I'm building a compiler, I'll be merging this along with the YARC. So in that case, I can give some return messages to YARC, which will be working accordingly. Okay, so in the printer statement, here now I'm giving a printer statement just displaying that this is an erroneous input. The input has exceeded, the size has exceeded. Else it is a given, else a given token is a numerical value. Instead, if the token is an alphabet followed by alphabets or digits, it is now an identifier. YY text is nothing other than the recognized tokens lexeme. Lexeme is nothing other than the stream of characters. Okay, the stream of characters, if you want, you can print. And this is one another program. So this program now specifies, it's now going to do a job of when I'm having a line number, line counting also it specifies. See, I'm having a special character, I'm just displaying a message and also I'm returning. What is the difference between the previous 2 programs and this program? In this program, in each and every pattern, I'm having a return statement. The difference between return statement now you know that this rule section is converted into the LEX function. So LEX function, you know that since it is a function, when you have a return statement, what happens? The command will go back to the main function which called LEX. So when I'm having a return statement, the given particular program will only process one single token. Okay, your program can be having a set of tokens, 100 tokens your program can have, but once it read the first token, it will return back. When you want to process the second token, again we have to call LEX. See here in this program, the program or continuation you are having here. Within loop, LEX is called again and again. Within the do while loop, LEX is called again and again. Why it is required is in the previous case, the first program all, I have first program, second programs all, I have called LEX only once within main function. Because we don't have any return value, again and again we read the input. Okay, but once you have a return value, recognize only until the return statement. Again, when you want to do the token separation, you have to call back the LEX function, which will continue from the previous. Okay, so in this case, the program is now reading the input from a file and reading just displaying the messages corresponding for each and every token. This is one another sample program. The last part I have to deal with is a context sensitivity. So just I will give a small part about what is meant by context sensitivity. So context sensitivity is when I'm specifying a pattern, Not only the characters in the pattern can be used for differentiating them, the surrounding information also can be required for differentiating them. The surrounding information of a pattern is known as a context information. One small example, if I'm seeing, you know that when in a program, when we have operators, okay, we have an operator hyphen. Hyphen is normally taken as a subtraction operator. It can be also taken as a negation operator. Okay, but the compiler has to differentiate this hyphen is a subtraction operator or a negation operator in the lexical analysis phase itself. How it can do? It can be done with the help of the context information. So actually in for differentiating the subtraction and negation, we have to make use of the left context information, that is the preceding information. Left context is the previous information of the token. For example, when I'm having A minus B, it is a subtraction. When I'm having equal to minus B, it is a negation. So in this case, if the preceding token is an identifier, we can now understand that the given hyphen symbol is a subtraction. If the preceding is equal to operator, we can see that the minus is a negation. So this type of operation is known as left context information. Based on the surrounding left information, if the token is differentiated, it is left context sensitivity. Based on the right side information, if it is required. So for example, if in some languages, keywords and keywords can also be used as a names for identifiers. If I'm having in my program, if is a keyword, I want to differentiate that if is a keyword or if is an identifier. How I can differentiate? In my program, if in my if statement, the syntax is if followed by brackets. Within the bracket, I'm giving a condition. After the bracket, I'm having a then statement. In that case, if all these are following tokens only, it is to be taken as a keyword. Else, it is to be taken as a identifier. So in this case, is succeeding information or the right context information is required for differentiating whether it is a keyword or an identifier. So that is known as right context sensitivity. So here for matching a pattern, the right context information of the character succeeding the pattern is required. So the example I specify. When the keywords are not reserved, keywords to differentiate, we require the right context. One, the special character in LEX used for that is slash. Slash is a lookward character. For example, if I'm giving the expression here means a regular expression. Regular expression 1 slash regular expression 2 meaning the first regular expression is a pattern, the second regular expression is the context information. Only if the first regular expression is followed by the second regular expression, it is considered as a pattern match. If this following part is not occurring in the given input, it is not taken as a pattern match. See here, this example will show that. So this example now specifies the pattern if it is followed by set of characters within brackets ending with then only it is a keyword. In all the other cases, it is to be taken as an identifier. In such a case, you can see that this is a two character pattern. This is also a two character pattern, multi-character pattern. You can even match with two character pattern. But if will be taken as an identifier only when it is not satisfying this case. That is only when it doesn't have the right context information, then it is to be taken as an identifier. So the special meta character used for handling the right context information is slash. Similarly, the left context sensitivity can be captured by a special mechanism known as start condition. So the start condition explanation. Saranya ma'am, is the session over or session timing over ma'am?
Ma'am?
Session timing
Ma'am?
over ma'am?
Yes,
Is
ma'am.
the session? Okay ma'am. So the
Ma'am, can
last
you
part
hear
I
me?
have, yes I can hear you ma'am.
Yes, ma'am.
Is the last part over? This is the last part I have not completed. So shall I close the session? Or shall I complete?
1 minute, ma'am. We are having a
This is
delay
1 minute.
actually.
Yes, the last part I have. Yes.
Ma'am,
So
just
left
a minute,
con.
ma'am. We have a delay here. That's why.
Okay, ma'am. So previous time I handled this for 3 hours. So time was well enough for showing a demo and operating. Ma'am, can I resume? Can I resume?
Ma'am, can you hear me, ma'am?
Ah, yes, I can
Ah,
hear you,
yes,
ma'am.
ma'am. Ma'am, we just had a 2 minutes delay, ma'am. That's why I couldn't capture your thing. Okay, ma'am.
Okay,
So,
okay.
students, do you have any questions?
Yes.
If at all you have got any questions, please post in the chat. Okay. So, I don't think there is any question, ma'am.
Uh, okay, ma'am. Thank you, ma'am. Then I
Faculties,
will share.
ma'am, one
Uh,
minute. Was
uh,
students, the attendance link is being posted in the chat, and you can just it will be closed within 5 minutes. So, ma'am,
uh, yes,
ma'am,
ma'am. Then I will share the
yeah,
PPT.
ma'am.
I will share the PPT
Yes,
and
ma'am.
the
Yes, ma'am. Yes,
link of
ma'am.
the software, ma'am. Link of the software.
Yes, ma'am. Yes, ma'am. Yeah, yeah, ma'am.
Uh,
Because we are used with, we know that Alex will be working only on the Ubuntu or Linux platform, but we are
yes,
happy
we
to
can
know
also
that
do it in
we could.
Windows. We
Yeah,
can
this
also
is
do it
more
in Windows.
flexible. Yes, ma'am.
Uh,
Okay, ma'am. So, want I
Next,
on
if you
behalf
have
of the
together,
School
we
of
can
Computing,
actually instead of Lex, we can use Flux. Instead of Yak, we can use Bison.
Flex,
Both are equal.
Bison.
Flux.
Yes, yes, ma'am. Yes,
Both
ma'am.
are the
Yes,
same
ma'am.
only. So
Yes, ma'am.
that
So,
will
since our
only
time is very
help.
short,
Yes, I
yes, ma'am.
cannot
Yes,
show it
ma'am. But
here
it was a
anymore.
really wonderful session, ma'am, because we learned so many things like pattern matching and how the context and left associative grammars, all of those things, how to deal with it. It is all really new to us. And many of the students would
Mm.
have, they're working on NLP so that they'll have an idea when they learn this,
Yes,
they'll have
yes,
an idea of exploring more in
yes,
NLP, ma'am.
yes,
Yes, ma'am.
yes.
Yes, because we have given mini projects also for the students,
Oh,
and that many of them have taken such type of projects only.
okay, ma'am. It will be
Okay,
very
ma'am. Just a word of
advantageous for
thanks
me.
to you, ma'am. So,
Thank you, ma'am. Thank you.
yes, ma'am. Okay, okay, ma'am, on behalf of School of Computing, I express my gratitude to our management, chairperson, School of Computing, and heads of various departments, and a special thanks to our audit professor, Dr. Sridhar sir, my colleagues, and all the participants. And indeed, a very, very special thanks to Vanita ma'am, who has shed light on the LEX tool and introduced us to Flex and even Bison. And we just came to know about all the tools that could work on a more flexible environment. And this session is definitely useful and interesting. I think we can build over so many things over this session, ma'am. So we are eager to
Yes,
have more extended sessions on other compiler construction tools also.
yes,
Okay, ma'am.
yes.
And I would like to express my thanks to Rajkumar sir, who has supported us in live streaming this session. So he deserves a special mention in our session, ma'am. So thank you so much, ma'am. But we are looking forward for another opportunity where we can gain more knowledge from you, because the session was really nice for
Yes,
us.
if it is a one day session, we can have a how to construct a
Yes, ma'am.
compiler
Yes,
even
we have
using
got.
Lex and Yak.
Yes,
Yes,
ma'am.
I
Yes,
can do
ma'am.
that
This
like that
itself
also.
is a, yeah, yeah, ma'am. So people like you should guide us and help us in gaining more knowledge in such tough subjects. It's very useful, and how the real compilers are working, we can easily analyze from what you have told.
Thank you, ma'am. Thank you. Shall I close
Thank
the
you, ma'am.
session,
Thank you
ma'am?
so much, ma'am. Thank you. Yeah, ma'am. Yeah, ma'am. Thank you so much, ma'am. Thank you, ma'am.
Thank you. I'll mail you the materials, ma'am.
Yeah, ma'am. Please, ma'am. Okay, ma'am. Sure.
Thank you.